Hello and welcome back to CodeBlaze. So I have gotten a lot of requests for smooth terrain generation in Unreal Engine, and today we are going to do just that. So we'll be implementing the marching cubes algorithm today. So down in the description, I'll have a link to Sebastian Lang's video as he explains the actual algorithm in a much better way using some visual aids. Though it's for Unity, but the algorithm stays same. So I recommend you go watch his video first as I'll be focusing more towards the implementation side. So yeah, let's get started. So a quick note, I did some refactoring in the project, which will make it easier to implement these new generation algorithms. So both of our current chunk classes and also the new one that we are going to create today are gonna have some common code. So rather than copy pasting it everywhere, I created this chunk base class and all of these chunk classes will extend this. So this class is responsible for the common properties like size and the height map frequency. It also has the generate height map and generate mesh virtual methods, which our child classes will be implementing. It has some protected variables like the mesh and the noise object and the mesh data itself. And if we see the translation unit, we see that the mesh and noise objects are initialized here, and the generation flow in the begin play are also implemented here, as well as the apply mesh. So that makes it easier for us to create new mesh generation algorithms, as the only things we need to implement now in our child classes would be the generate height map and the generate mesh. So all of this code has been committed to the Git repo, and if you want this base class and all, you can just directly get it from there. Right, so now we'll create our new marching chunk class in the engine. So I have the engine open here and we'll create a new C++ class and we'll base it off chunk base. I'll just select chunk base here and I'll call it marching chunk. Marching chunk, and I'll just press create class and let it generate. So we'll come back after this is done. We'll go over what all properties we are going to add, some private variables, functions, and a lot of constants. Yeah, see you back. So I have my marching chunk class created here, and the first thing we'll do is define some U properties. And the first one would be the surface level. So I'll do edit defaults only. Category would be marching cubes, and surface level will basically tell us how much of the mesh should be inside the surface or outside. By default this would be a value of 0, but we can change it as and when required. So surface level, I'll do 0.0f. The second U property would be a Boolean flag, which will tell us whether to use the interpolation or not. So if interpolation is used, we'll get a smooth result, and if it's not used, we'll get some angular or blocky kind of result. So I'll just define this U property. Again, this is edit defaults only. Category would be again marching cubes, and this would be a bool interpolation, and by default I'll have it as false. You can have it as true, so that's up to you. Finally, we'll need our overriding members, so I'll get that here. And down below in this list, we'll have our generate mesh and generate height map methods. You can just do this, and I'll create the definitions also for both of them. Right, so we have definitions for our protected methods, and next we are going to take a look at what all private variables and the private functions we require, and also the constant data which marching cubes heavily depends on. So I'll create the private block here, and the first private variable would be an T array. So we'll do T array of floats. So this is where we'll basically store our voxel values. So I'll just call it voxel. And next we need a int array, and this is where we'll store the triangle order. So why we require this will be much more clear when we use it, but basically depending upon the surface value, we'll need to create triangles facing in inside or outside direction. And after that is decided, we'll be using basically changing this triangle order so that triangles are created correctly. So for now, you can just create a array here, triangle order, and the length we need is of 3, and we'll give it a default value of 0 comma 1 comma 2 here. So the default value would be of triangle 0 1 2, and if surface value is something else, we'll reverse this. That would be 2 1 0. Right, so these are the only two private variables we require. Rest of all are already there in our base class. And next we'll define our private functions. So first would be the actual marching method. I'll call it void march, and this will take in the position. So int x comma int y comma int z, and it will also take in the voxel values of the current cube. So we will pass in that by using an array. So I'll have const float cube. So cube has 8 vertices, so we'll have a float array of length 8, and using this we'll be passing the 8 corresponding voxel values for the given cube. Next we have the array flattening method, and the reason I didn't add this in the base class is because the logic for matching cubes will be a bit different, and I'll show it once we implement it. But for now we'll just add the definition here, get voxel index, and this will take in an int x, int y, and int z, and this will be a constant method as it won't change anything. And finally, we'll have a float method here called get interpolation offset. And this method will be used when this flag is turned on. And it will basically return the interpolation value between two floats so as to generate smooth terrain. I'll just call it get interpolation offset. And this will take in two float values. So float v1 and float v2. And this will also be a const method. So with this, we have all our private functions defined. So I'll just create the definitions for them. And the only thing remaining now is to define our constants. So that is what we'll take a look at next. So marching cubes heavily depends on some constant data, and I'll have a link down below of a GitHub gist from where you can also copy this data. So I'll just copy it here and we'll paste it here. So now I'll explain what basically all this data means. So from the start here, we have the vertex offset array, which basically represents the 8 vertex positions of a cube. Then we have an edge connection array, which tells us which all vertices are connected via an edge. And we have the edge direction array also. So this basically gives us the vector direction for each edge. Finally, the two big ones are the cube edge flags. So this is what we will be querying with the voxel values of the current cube to get which all edges do we need to consider for generation. It will be more clear once we actually use it and you see how this is used. And finally, we have the triangulation table, which has the basically all the combinations or the different types of triangles that can be created from a given cube, and there are 256 of them, but actually there are only 14 unique combinations. Rest all are just variations and different orientations of these 14 combinations. So if you watch Sebastian Lang's video, it is more clear there, and he actually shows the 14 combinations also. So I again recommend going through that once. But this data is something you'll generally copy paste. You can come up with it on your own if you have time, but Yeah. So that's it for the definition part. We have everything we need in our header file. And now we can start implementing these 6 methods. So let's get started. So before we jump into the implementation part, there is one thing I want to make clear. So marching cubes will generate the mesh inside the bounds of the chunk. If we consider this illustration, which is basically 2D marching chords, and these solid black lines would be the bounds of the chunk. You can see by default it will create a mesh inside this. So when you have multiple chunks spawned all around, you'll have these gaps in between. So to overcome this, we'll need to store voxel values in each direction till size plus 1, as you can see here, and generate the mesh also till that bounds, so that all of our meshes are clearly stitched together. I hope this illustration makes what I'm trying to convey clear. And this is the reason why the constructor and the get voxel index is going to be a bit different than our existing chunk classes. So let's get on with it. So in the constructor, we'll initialize the voxels array to the cube of size plus 1. And to do that, we'll basically call voxels dot set num, and we'll have size plus 1, and this is what we'll cube it. So we'll have this 3 times size plus 1 into size plus 1. Now our get voxel index or the flattening function should also respect that. And basically what we had earlier, we'll do the same. Instead of size, we'll pass in size plus 1. So I'll have return z into size plus 1, size plus 1 into bracket of size plus 1. Similarly, I'll add in the y value, which would again be multiplied by size plus 1. And finally, our x value. So with this, we are storing voxels around the chunk also, one block around the chunk, and with the flattening index, we'll be able to access that outside values also. Next, we'll look at the height map here, and yeah. So this time, instead of generating a 2D height map, we'll be generating a 3D height map, as that would give us a more interesting result. But if you want a 2D height map, you can go ahead with that. So the first thing we do is store the position of our current chunk. So const auto position. This would be get actor location, and we'll divide this by 100 since we want the unscaled units. And I need to add an I here. So next we'll be iterating over the voxels array. So again, our 3 for loops, 3 nested loops we'll have. And finally, we'll be setting the voxel value here. So that would be voxels, and again the flattening method, get voxel index at x, y, z, and this would be equal to noise. So this noise object already exists in our base class. So noise dot get noise, and you can see there is an overload with 3 arguments also, and that will basically return us 3D noise. So we'll use this one. So we'll basically pass x plus position dot x, then y plus position dot y, and finally z plus position dot z. And with that, we basically have our 3D height map generation done. One thing to keep in mind is that this get noise function returns a value between 0, basically -1 and 1. So that is perfectly fine for us. And next, we'll finally start with the generate mesh method. So in generate mesh, the first thing we'll do is figure out our triangle order depending upon the surface level. To do that, we'll have an if condition here. So if surface level is greater than 0.0 f, we'll have a different triangle order. So that would be 0, 1, 2. I'll just copy it here. And else, we just reverse this triangle order. Again, I'll copy it over. So this would be 2, 1, 0. So this way we'll have triangles facing in correct direction irrespective of the surface level. And finally, this triangle order will be used when we actually populate the mesh data, and this triangle order will be added as an offset. So next we'll define a float array which will store the voxel values for the current cube, and we'll pass it on to the March method here. So to do this, we have our float array here called cube, and this would be of length 8 here, since we have 8 vertices. Then we basically need to call the March method for each cube. So we need to iterate over the voxels array again. So I'll have this in nested loops, and inside here we need one more loop to populate this cube array. So I'll have a for loop, but this will run till 8 only, since we need 8 vertices. And we can basically say cube I will be equal to voxel dot, and we'll use the get the flattening method here. And this would be equal to x plus the vertex offset, since this is how we'll get all the 8 vertices. Vertex offset of I comma 0. So 0 would be the x index, and then we'll have the same thing for y. So y plus vertex offset of I comma 1. Next we'll have z plus vertex offset of I comma 2. Right. So after this for loop, we'll have our cube array populated. So we can basically call our March method here. So March will be called with x comma y comma z comma the cube array. So now we just need to implement our March function and the interpolation function. So let's get on with it. So in the March function, the first thing we'll define is an int variable, which will be the vertex mask. And this is where we'll store what all vertices are inside the surface. So vertex mask, and we'll initialize this to 0. And we'll define another array here, vector array, f vector array called edge vertices, edge vertex. So these will be the vertices that will be actually considered for the mesh generation. So this will be populated according to the intersecting edges. So this would be of length 12 at max. So I'll define it with the length 12 here. And the first thing we need to do is compute the vertex mask. And to do that, we just need to check the 8 cube values, what all are less than the surface level. So we'll do a for loop here till 8. And if cube I is less than equal to the surface level, in that case we'll add basically shift the vertex mask by 1. So or equals 1 left shift I. So this way the correct bit would be set in a vertex mask corresponding to the cube, right? And next we'll define our edge mask. So that would again be something that will be used later. So the edge mask will basically be computed using those cube flags, cube edge flags constant array. So we'll pass in the vertex mask and get the edge mask. And edge mask represents what all edges are actually going to intersect the surface. So this would be constant edge mask, and this would be our cube edge flags, and we'll pass in the vertex mask. This will return us a mask which will have bits set as 1 for the edges that are going to intersect the surface. And now we just need to iterate over the edges and find out which edges intersect and create the edge vertexes out of them. Before we iterate over the edges, we can check if the edge mask has a value of 0. In that case, we can simply return, since in that case there is nothing to be drawn, or it's an air block basically. And otherwise we will iterate over all the edges here. So for I till 12, we'll first check if the current bit is set in the mask for the given edge. And to do that, we'll have edge mask and 1 by left shifted by I. And if this is not equal to 0, we know that this bit is set. And now we can basically compute the offset value. That would be const float offset, and this will depend upon whether the interpolation flag is set to true or false. So we'll use the interpolation flag. Conditionally, we'll call the get interpolation offset method with the two values that are going to be the voxel values for the current edge. So each edge will have two vertices. So we'll basically be passing the voxel values of those two vertices. And to get that, we'll use the cube array here. Then we'll check the edge connection, since we want to know what are the two vertices of the given edge. And we'll pass in the I and pass in 0 here. So that would be the first vertex of the edge. Next, we'll have edge connection again for the second vertex. So I comma 1. And with this, we'll get our offset value if interpolation is enabled. And if it is not enabled, I'll just set it as 0.5. That gives it the angular or the blocky look. So now we'll implement this get interpolation offset method, and this is pretty simple. So we'll have a const float called delta, and this will be equal to v2 minus v1, and we'll return delta. If delta is equal to 0.0f, in that case we'll return the surface value, which is the surface level. Else we'll return surface level minus v1 upon delta. So that's basically how interpolation works. And with this, we'll be getting offset value, which will be more close to the stronger voxel value. So that way you'll be getting a smoother terrain. Right. And yeah, so next we just need to add the edge vertices and finally fill in the mesh data. So now we'll fill the edge vertices, and to do that, we'll take the edge vertex array for the ith vertex. The x value would be equal to x plus vertex offset, and to get the vertex offset we need to know the vertex, and that we can get to know from the edge connection. So edge connection, and we'll take the ith value, so the first vertex of the edge, and from the vertex offset we'll take in the x coordinate, and to this we'll add the offset multiplied by the second vertex of the edge. So edge direction, or basically shifted using the direction, not the second vertex. So we'll basically add that offset in the given direction. This will get from I comma 0, since we need the x value only. Right. So this is for the x, and we'll just duplicate this. I'll change this to y, this to z. This will become y, this will become z, and these will change so that they use the correct coordinates. And with this, we have our edge vertices computed. So we basically now need to iterate over these and add in the triangles to the mesh data array. So if you've looked at the illustrations by Sebastian Lang, you'll know that at max only 5 triangles can be created for a given cube. So that makes our work a bit easier. So we'll iterate 5 times for I till 5. And if at any time we see the triangle table, so triangle connection table, given the vertex mask and the current triangle, so that would be 3 into I, since each triangle has 3 vertices. So if this is less than 0 at any time, we can simply break. And if you actually look at the triangle table here, there are quite a lot of values which are -1. So that means a triangle shouldn't be drawn there. And if we reach that, so we can basically break it out, since these -1s are at the end only. If not, we can create our vertices here. So first we'll find the 3 vertices that are going to be added to the mesh data array. So I'll have an auto v1 here. So this would be the edge vertex. And to get the correct vertex, we'll again use the triangle table here. So the triangle connection table will pass in the vertex mask. So the vertex mask and the vertex of the current triangle. So that would be 3 into I. So this 3 into I basically represents that for each permutation, there are 3 triangles, right? So this is a flattened array in a sense of second dimension 3. So we get a vertex here, the V1 vertex, and we will multiply this by 100 to scale it to the unreal units. So I'll duplicate this twice to get V2 and V3. To do that, we simply need to add 1 here. So this should be I not 1. So I plus 1 and I plus 2. Right. So with this, we have our 3 vertices. And the next thing we'll do is compute the normal here. Now, if you remember your high school mathematics, to find out any plane, we basically need 3 points. And using these 3 points, we can create 2 vectors which are along that given plane. And if we take the cross product of those 2 vectors, we'll get a vector perpendicular to those both. And so if this doesn't make sense to you, just basically see the definition of what a vector cross product is and how we can represent a plane using 3 points, right? So I'll have a variable here called normal, and this will basically be an f vector cross product of v2 minus v1 and v3 minus v1. So v2 minus v1 and v3 minus v1 are the 2 vertices along the plane. And when we take a cross product of these two, we'll get a vector which is perpendicular to these both. So in a sense, perpendicular to the current plane. And that is what exactly the normal value is. So we'll basically normalize this to get a unit vector. So that is what we'll be adding to the mesh data. The only thing pending now is to add the mesh data. So I'll just copy this since it's repetitive stuff. We add the 3 vertices, then we add the triangles. So here we'll be using the triangle order to specify the correct offset of the triangles. And finally, we add in the normals. So note, I'm not populating the UVs currently, since that is a bit more complicated, and I'll keep it for a later video. And finally, we increment the vertex count by 3. So vertex count plus equals 3. Since this vertex count is again used here in the angles array. So with that, we have our marching cubes pretty much implemented. So I'll just compile and let's see if it works the first try, which I doubt, but it will be miraculous if it works. And yeah, so see you then. So my code just compiled and I'll create a blueprint out of our marching chunk class. so that we can easily change the values without recompiling. So in all class, I'll just search marching chunk, right? And I'll call this BP underscore marching chunk, right? And so we can open this blueprint, and this way we can easily toggle on and off the interpolation. First, we'll test without interpolation. So I'll just check all of my values are here. Right, so interpolation is turned off. So I'll just compile and save it. Go back to my main map in the chunk world. I'll change this to use the BP marching chunk, and I'll enable the draw 3D. So this will basically draw the chunks in XYZ coordinates. That way, if you are using a 3D height map, that would be much more easier to view. And we don't need a much bigger draw size since the chunk size is already 64. So I can just say draw distance as 1. So if I just play and hope the editor doesn't crash, and it crashed. So let's figure out what's wrong here. So I figured out the issue, and if you found out before me, so that's good for you. Like you're actually paying more attention to what I've been saying than myself. So basically, we are generating the size here till the size. Basically, we have an equal to here, and that is correct. But in case of our mesh generation, or when we need to call our march method here, we should not take it to the last bound, since the last bound will automatically be added using these vertex offsets. So if we run till x, till size, and vertex offset adds 1, we are already at size plus 1. So we were going even higher, so we are going till size plus 2. So I'll just remove these equal to signs here, and I'll just compile and start the engine again, hoping that's the only issue. So with that fix, I just compile my code, and now if I press play, hopefully it runs properly. Yeah, so we have our marching cubes algorithm working. So this is the angular look that I was talking about. Since currently there's no interpolation happening, everything is offset by 0.5. And on a personal preference, I like this look a bit better. But if you really want the smooth result, you need to enable the interpolation. So we can go back in our blueprint and open the marching chunk. And we just need to enable this interpolation and save this blueprint. Now if we press play, we will be getting the smooth chunks, as you can see. But these also are not totally smooth, and I would call this like flat shading. And the reason we are getting it this way is because we are calculating face normals instead of the vertex normals. So currently the normal values for all the 3 vertices are same, hence we get this flat shaded result. But if you compute the vertex normals individually for all the 3 vertices, then the shader would basically interpolate the normals along the face, and that would give you the true smooth result. And that is something I'll take a tackle in some other video. But for now, if you want to do it yourself, you can just search basically creating vertex normals in marching cubes. It's a bit more complicated than what we existingly have. But if you're going for some kind of a low poly look, I think this should be sufficient, this flat shaded results. So that's it for this video. And there's a few things I would like to talk about. So if you have been following the series, and I would really love to see your results also. So you can just upload some screenshots to Imgur and put a link down below in the comments. Or you can directly DM me on my Insta profile. So I have a link to that also down below. And next thing is like I'll be starting another series. So this would be a proper beginner friendly series in Godot, creating the color switch game. And yeah, that's it. So these two series will kind of go in parallel, as there is not a lot more to cover here in the mesh algorithms or the terrain generation part. Some more algorithms like isosurface extraction or dual contouring or we can improve the current greedy meshing algorithm also that we have here, like add UVs and baked ambient occlusion. So all that stuff we'll cover, but I want to focus a bit more on the Godot series since it will be a change for me also. So yeah, so if you enjoy, just leave a rating down below. If you have any other feedback or any other requests, leave them down below in the comments. If you like the series, I don't mind, just share with your friends so the channel grows a bit. And yeah, thanks for watching. Bye.